Okay, good morning, everyone. So we'll start with our lecture. Okay, any questions so far? Any comments before we take off? Okay, so we'll take off. Okay, so we were discussing convergences last time, right? That's where we ended. So LP convergence, everybody understands. It's one of those concepts it's good to drill in. So first we define a probability space omega. On that we have collection of subsets, the calligraphic F, the sigma algebra. On the sigma algebra, we define a probability measure, right? P. Now on this, we can define random variables, measurable functions, right? Now all the measurable functions that we define, whose absolute values raised to power P, that moment is finite, these are said to belong to the space LP. So LP is a space corresponding to the underlying probability space omega FP. That will be clear on that. Huh? Now, you can say that Xn converges to X in LP sense if this quantity right here goes to 0, right? Absolutely Xn minus X raised to power P in expectation goes to 0. And this one can define as the norm in LP space. And as we discussed, that it has this nice property that it satisfies the triangular inequality. And it's 0 when X is 0 almost surely. All right. So that was one idea. The other idea was convergence in distribution. So we say Xn converges to X in distribution if the CDF of Fxn converges to CDF of X at every point of continuity of F. So if F happens to be discontinuous at some point, then this convergence need not hold. But at continuity points, this should hold. Then we say we have convergence in distributions. This is when your X is defined in single dimension. Right? So this is what we mean here. But you can show that this is equivalent to, so this requires a proof, that expected value of bounded continuous functions f of xn, that converges to expected value of f of x for all such f, right? So this corresponds to that and that corresponds to this. This requires a proof. But the nice thing about this way of defining convergence is it extends to general random elements x. X need not just be a random variable, it could be a random vector. It can be a process, and we can say process means collection of random variables, and we can say sequence of collection of random variables converges to another collection of random variables in distribution if the following property is true. So great generality is achieved in this manner. All right. Later, this comes up, for example, when we talk about Brownian motion, and we show Brownian motion as a limit of sequence of random variables. Sequence in the sense of continuous sequence. All right. So some relationship we discussed last time, L2 convergence does imply convergence in probability always. L2 convergence does not imply almost sure convergence. Almost sure convergence, as we discussed last time, implies convergence in probability, but convergence in probability does not imply almost sure convergence. So all this is clear. So let's do some example of this. So now again, we want to show that Xn converges to X almost surely, but not in the sense of LP, right? So we'll look at this space again where we saw last time. We actually seen this example for L1. So omega is 0, 1. Xn omega is n if omega is between 0 and 1 by n, and it's 0 otherwise. So Xn omega for all omega not equal to 0 is converging to 0 eventually. On that omega, this sequence x1 omega, x2 omega, so on and so forth, will eventually become 0 and stay 0. So that means Xn is converging to 0 almost surely. Right? This is happening almost surely. On the other hand, E of Xn is equal to 1 for all n. So Xn is converging to 1 in the LP sense, but it's not converging to 0. And so this is not, so Xn is not converging to 0 in L1 sense. Let me just check something in my mind. Okay, I'll have to check if xn is converging to 1 and L1 sense. Maybe it is, maybe it isn't. That's not immediately clear. But in any case, it's not converging to 0 in the L1 sense. The result can be extended to LP space for arbitrary p if you set p arbitrary p greater than equal to 1, if you set xn equal to n raised to power 1 by p, right, for omega between 0 and 1 by n. So the same argument goes through. All right, let's now consider an example where xn converges to x in L1, but does not converge to x almost surely. And suffices to consider the example where xn converges to x in probability, right? You can argue that if xn converges to x in probability and xn is uniformly bounded sequence, then it also converges in L1. So this should not be surprising that this converges in L1 in this case. And it doesn't converge almost surely because we saw that last time. So let's just go through this experiment one more time just so that you're reminded of it. Recall that we were moving around the circumference of a circle. Circle had a circumference of length 1. C0 was 0. Cn was Cn minus 1 plus 1 by n mod 1. Right? Xn was indicator of lying between Cn, omega lying between Cn minus 1 and Cn. So you can see that Xn takes value 1 on a set of measure 1 by n. Right? So Xn is equal to 1 with probability 1 by n. It's equal to 0 otherwise. So expected value of Xn now is 1 by n. So this limit here is 0. Right? So Xn is converging to 0 in L1 sense. Right? But Xn is not converging to 0 almost surely. Because again, on every omega, Xn is not converging to 0. Because Xn is 1 infinitely often on every omega. Is this clear to everybody or should I? Any issues with this? Tika, again, this is your space. 0 here, 1 by 2 here, 3 by 4 here, 1 by 4 here. Take any omega here. Your Xn is like, it's random variable, which is 1 here. Then thereafter it's 1 here. Thereafter it's 1 here. So on and so forth. It'll go on like this. Slice will be of length 1 by n. That 1 by n slice will cover every point infinitely often. So xn omega will become 1 infinitely often at every point. So xn is not going to converge to 0. All right. Okay, now let's do quickly law of large numbers. So let's prove it. I've been mentioning it earlier. We first do weak law of large numbers. So suppose x1 through xn are independent, identically distributed random variables. They're IID with mean mu and variance sigma square. Let's assume that the variance is finite for this sequence of random variables. Define Sn to be sum of n random variables, first n random variables. Then the law of large numbers says that the average Sn by n, when you center it by mu, when you take the mu away from it, that is converging to 0, meaning in absolute value, the fact that it's greater than epsilon is going to 0 as n goes to infinity. So technically, what are we saying? We are saying that Sn by n is converging to mu in probability. Right? So we have convergence in probability here. So that's how law of large numbers was defined earlier. We said it repeatedly. So convergence in probability. That was an understood concept. Almost sure concept was a new one. Sigma square, everybody understands, right? Variance of x. It's just expected value of x centered, square of that centered, and that's just this quantity right here. All right.
Okay, so one basic question.
Mm-hmm.
We're saying x1 to xn are IID random variables with mean mu and variance sigma square.
Right.
Are we inherently assuming that it's normally distributed?
Not at all.
But then how would you represent other distribution in terms of distribution?
I think you're kind of linking it to the fact that sums of arbitrary IID variables begin to look like they have a normal distribution. And that's what you're thinking. That's the central limit theorem. That's the next topic. But yeah, it's good to keep in mind that in the central limit theorem, the individual x1, x2, x3 can have arbitrary distribution. Nothing to do with Gaussian. Sum begins to look like a Gaussian distribution. So that's an important point. Okay. All right, proof of weak law of large numbers. So it's an easy statement, so it should have an easy proof. Let me give you that easy proof. So let's look at Markov's inequality. How many of you have seen Markov's inequality before? How many of you are seeing it for the first time? For the first time. Okay, everyone's kind of heard about Markov's inequality. Okay, we have this probability that x, non-negative random variable x, exceeds a. Oh, there we go. Yeah. And that's upper bounded by expectation of x upon a. And the proof of this is straightforward. You all remember? E of x is nothing but this integral. And just so that we are clear, d fxx, you should think of it as integral with respect to induced measure by random variable x, mu x. Because the random variable is inducing a measure and a distribution function. Okay, so it's very generally defined. All right, so you have this quantity here plus this quantity here. So this inequality follows. And then this result follows, right? A is just a constant here. All right. So now how do we prove the weak law of large numbers? Anybody? You've seen some of this stuff before. We can use Chebyshev's inequality. So we can consider probability of x minus mu an absolute value greater than a. Now it's a non-negative variable, right? Because we take an absolute value. Equivalently, we can square both sides, nothing changes. It's one-to-one mapping. And this we can write just from Markov's inequality as variance of x upon a square. So we have this now, right? Okay. So we apply this to this quantity right here, Chebyshev. That's all. So everybody with us on this? Now variance of Sn upon n is what? I mean, what's nice to know is that variance of Sn, variance of the sum is equal to sum of variances when the variables are independent. This will be n times sigma square. 1 by n will come out as 1 by n square, right? So we get this quantity right here. And this tells you that's why the order is important. Epsilon is fixed, then we're letting n go to 0, n go to infinity. Not like first let fix n and let epsilon go to 0. That'd be a different problem altogether. So we're saying for all epsilon fixed, this probability here should go to 0. And that we achieve from right here. So that's your weak law of large numbers. Any questions on this? Pretty straightforward. Dhruman, I can move the slide. Okay, good. I'll move the slide. Okay, so now let's make it something less straightforward.
So can Markov inequality implies Chebyshev or Chebyshev imply Markov inequality?
Markov implies Chebyshev. Okay. Just because we use Markov here to prove Chebyshev.
Okay.
Right? But Chebyshev holds when the variance is finite. Markov is true even when variance is not finite. Expectation has to be finite.
Okay.
Right? Because when we squared things here, then we require the variance to exist for the right-hand side to be well defined. Otherwise, it's of no use, the upper bound. But really, what you should remember is kind of that they're both using the same idea for proof. You just decompose the expectation to two terms, and then these results follow.
This and doesn't prove it for unbounded gate. So
Yeah, for infinite
not-
variance. For infinite variance is what you mean. I mean, sigma square has to be finite. Unbounded means what? Either variance is finite or is infinite. So for infinite, it doesn't say anything. So what's your question? Sigma square is finite, right? Statement Chebyshev says, well, in the LLN and variance sigma square finite. You missed the bracket. Okay. Can't miss the bracket. All right. So now let's do some stronger stuff. Strong law of large number. So we'll actually show that Sn by n converges almost surely to mu. But we'll assume the fourth moments of each xi is finite. And actually we'll assume it's bounded. Right? In reality, the proof is true even with just first moment being finite. But that requires much more effort to make that proof work in that generality. So this is a much simpler proof in the fourth moment, and you'll see why. So everybody with me so far? So you want to go back thinking that strong law of large number holds. All you need is that the first moment is finite. That's it. I mean, absolute value of x times log of 1 plus x, 1 plus absolute value of x, in expectation could be infinite. And still strong law of large number holds. And same thing with for weak law of large numbers. Just that the proof I gave you assumed that the variance was finite. But it's true more generally.
That is the second.
That's right. That's right. Yeah. Okay, so I'm going to assume that mu is 0. This is without loss of generality. I'll just subtract mu from every random variable. And I'll assume that the fourth moment of xi to the power 4 is each chi is bounded by k. Now, each xi need not be IID in this case. They just have to be independent with mean mu, same mu. And now with mu removed, mean becomes 0. Okay, what I'll do is I'll just look at this fourth moment here, right? Sn to the power 4. That's just this quantity right here. We can open this up, right? When you open this up, you'll have some terms involving xi to the power 4. You'll have some terms involving xi to the power cube times xj, right? And you'll have some terms involving xi square, xj square. All the terms where xj comes independently alone with power 1 to it, when you take the expectation, it becomes 0. Because see, if I have terms of the following four, e of x1 cube x2. So what is this equal to? They're independent. Hmm? 0, right? Because expected value of x2 is, in this case, is 0. So all the terms where x shows up with power of 1 on it, those terms vanish. So only terms that remain are ones with fourth power or with second power. And then e of xi square, e of xj square. Okay. What's that? Yeah, Aman will explain.
One of them why construction? But see, x2 we don't know, but x we know is b2. And by construction, for one we are assuming b.
Right. Yeah, I think, okay, there's a tiny bug here. Doesn't affect the overall proof. Let's just assume for now that each expected value of xi square is same for all I.
But IID, that's true.
No, so I was trying to say we need not be IID. This proof works with just this property right here. Independence in this. No.
I mean, it's like what
I mean, if I can give you something more general, why are you upset?
no, I'm not upset. SN now was defined as ID, but now we're saying SN can be defined as
Yeah,
any sample.
that's it. That's it. Yeah. Yeah. SLN can be defined more generally than IID, but you have to put some assumptions. All right. But the point is here, I put xi square, the whole square. So what I mean is xi square times e of xj square, I and j are not equal. That will occur, 3n minus 1. That's the different ways which we can pick them.
I see. So this is just summation over I not equal to say.
I not equal to j, yeah. And that's all I really need here, right? But because I'm assuming e of xi square is same as e of xj square, I can write it like this. Okay.
I know like this n x I to the power 4 is in summation. So that's just summation I over e.
Yeah, yeah, yeah. Yeah, so this is, so here I've assumed that they all have the same moments in this, just to write things nicely. Okay. Yeah, let's just assume they have the same moments, fourth moment as well as the second moment. And your homework becomes to generalize them. Okay. So then by Jensen's, you know this. Can you prove this to me immediately?
X square is convex.
Yeah.
Not K.
Convex. Got it. Yeah,
X
yeah.
square is convex. It is convex.
Yeah, well, I mean, you could go that way, and that will require a little bit of work. But can you just see a more immediate argument why this is true?
Why was that now?
Huh?
Jensen.
I mean, you'll have to take x to the power 4 being convex and then kind of somehow squeeze it. Yeah, so you have to call y equal to x squared.
Yeah.
And then y squared is convex. Yeah, that's how you can do this.
Yeah,
Sure. Yeah, that's the more of the argument. Yeah. No, but do you need to do that or you can see it immediately? Huh? Well, it's a variance of xi square, right? So variance is always non-negative.
So, but why is that less than equal to? Because people are like the variance of x. Why is the variance square less than equal to x square?
Not variance square, variance of xi square. Variance of any random variable is non-negative. Okay, yeah. So it's expected value of fourth power. So yeah, you don't really need Jensen's inequality here.
X square.
Yeah. Variance of x square is non-negative.
Just take
Yeah.
x square.
That's all, yeah.
Oh yeah. But why is x square? But taking left hand side, that's how you define variance.
Yeah.
Oh.
Your telepathy is not working very well. Feel the force. Okay. Yeah. So let's carry on. Huh? All right. So then you get that, okay. This you get here, right? NK3 and N minus 1. All right. And then,
And this comes from the assumption that we have assumed that expectation of all the movements of x is same.
yeah. Yeah. I mean, fourth moment and the second moment. But you can prove this bound you can get more generally. 3n squared by k. So we've got n squared on the right-hand side, huh? Well, that's right. If you already understood it, then why would I be here and you'll be there? We'll have to wait for next. But we got this bound, right? All right. Yeah, you want to take a crack at guessing what's nice about n square? Not so easy to guess, huh? These are things, a lot of these things are things you have to see once to guess the next time. It's no, it's yeah. You're not at that stage. I mean, I give you a few thousand years, you still won't get it. This you get? So I could divide Sn by Sn to the power 4 by n to the power 4, right?
Yeah.
Huh? So now we are talking about something which we understand. Sn by n has made an entry. Okay, but it's not so obvious how to come up in this direction, right? If you've not seen these things before. Well, 1 upon n square, what's nice about 1 upon n square? It converges, you can sum it up. So in this case, again, these are not ideas which are so obvious. You have to kind of see them. So I'll just take summation on both sides. And I get that the sum is finite. So this is a clean way of doing things.
Summation
Over n.
N.
Over n.
Yeah, so different SN, like S1 plus
Sure. Yeah. Expected value of Sn by the way. Yeah, no, these are not so straightforward things. You could come up with your own argument, but it'll be more messier than this. This is a clean argument. It's just good to see it. Okay. Now this tells you that this whole summation is finite, and we can replace expectation and summation. So one way is because everything inside is non-negative, so we can always replace expectation summation. That's Fubini's theorem. I'll just mention it in a moment. Okay. This immediately tells you that the underlying random variable inside the expectation should be finite almost surely. Because if it was infinite on a set of probability measure positive, then the expectation will be infinite. Right? Just this. If E of z is finite and z is non-negative, then z must be less than infinity almost surely. Because if z is not less than infinity almost surely, meaning z is equal to infinity with positive probability, then the expectation becomes infinite. Okay? So this immediately now tells us.
And if Z is infinite with some zero probability, then we just won't count.
Yeah, that doesn't matter. So that gives us this quantity right here. So this summation here is finite. Well, because in expectation, we can't say what happens on set 0, right? I can give you another random variable which is infinity on rationals. The expectation will be unchanged. So if I tell you expectation is finite, that just means that the random variable is finite. Almost surely. Random variable still can be plus infinity at points of measure 0. Okay. So, I mean, that's the whole point, that if I give you this quantity, E of z is less than infinity for z greater than equal to 0, all that tells you is that z is less than infinity almost surely. Is this kind of clear to you guys who are seeing this for the first time? Okay. Now, I claim from here that this must be true. Can you see this?
Yeah.
Same reason, because this implies that on every omega on this set, Sn by n to the power 4 its limit is going to be 0. Right?
Because the sum converges.
Because the sum converges. Yeah. I mean, if this was greater than some epsilon infinitely often, then the sum will not converge on that omega. Is this point clear to everybody? It's a little subtle point, yeah.
I mean, somehow standard that sequence converting implies.
That's right. So the term must be going to 0, because if term was not going to 0, then you have a problem. Yeah. Now, what's true for fourth power is also true for 1/4 of that power, right? Even that must be going to 0. So you can see it's a little kind of convoluted proof. But on the other hand, you didn't have to use Borel-Cantelli or all the other ways of doing things which will be more intricate. It's kind of, in some sense, it's element.
To assume that Sn by n is positive.
No. Just Sn by n to the power 4 is positive.
But then that one.
Sn by n to the power 4 is going to 0. Sn by n can be positive or negative, must also be going to 0.
Oh.
Right? It can't be that Sn by n is negative and not going to 0. And Sn by n to the power 4 is going to 0. Okay. Everybody with me on this? All right, so we got law of large numbers under our belt. So we won't prove it any more than in any more depth than this.
How long does it take for a quiz to this?
Foolproof or foolproof? Okay. Foolproof, if you look at Kyle Lai Chung course in probability theory book, it takes 2.5 pages to prove this. Kind of, yeah, just on the moment assumption. But if you were to use martingale theory, fully developed martingale theory, it takes two lines. But then you have to build up a lot of machinery to get there. But that's the power of martingale machinery, that you can prove a lot of complicated things very, very simply. But that we won't cover in this course. We won't get time to. ठीक है. So far, so good. Any questions online? All right, so let's carry on. Central limit theorem, our friend. Okay. So I'll just walk you through some ideas here. I won't prove the more in-depth things here. There are, of course, extremely elegant results and complex results in the sense they require complex number. But what also is kind of interesting about when you go in the complex world is your intuition kind of gives away. Up till now, everything I said, you could kind of intuit it. But that's why I don't like complex numbers. So x1 to x2 are IID with mean, mu, and variance finite, sigma square. Sn is as before. Central limit theorem says that this guy here, Sn by n minus mu, is going to 0. But then the question is at what rate? I mean, so law of large numbers says that this is going to 0. And the question is what rate? So the way to answer this is you multiply by something which is going to infinity in such a manner that the product is non-trivial, is going to a non-trivial limit. Okay? And that's what central limit theorem does. It essentially tells you that Sn by n looks like mu plus sigma by root n into z, where z is normal 0, 1.
Wait, how does one make sense of some unit multiplied by infinity? And that's going to some non-trivial finite.
Yeah, so one thing is going to 0, the other thing is going to infinity. Together, they are going to something non-trivial. That tells you the rate at which something which was going to 0 was going to 0. That's a great question, yeah. So everybody with us on this, you can see this kind of... so intuitively, this is very nice. It kind of tells you that, in probability, we can't say anything about the random outcome. But if you have many random outcomes from the same distribution, independent, then the sum begins to look more and more deterministic, right? So there's certainty that kind of can be captured from the sum. Yeah. Sorry? Yeah. What's the purpose of it? Well, it's kind of, that's what I'm coming to in a way. So Sn by n, law of large numbers says that it looks a lot like mu, the mean, right? But then you say, okay, what is the error? And root n tells you that the error is some constant sigma, which is kind of inherent to the noisiness of xi, divided by root n into normal 0, 1 random variable. So it tells you that all the action is in the neighborhood of 1 by root n of the mean. That's where most of the mass is of the central limit theorem. For the distribution sum. I mean, all of your statistics is kind of based on, building confidence intervals, which relies on the central limit theorem in this sense. So root n is crucial for that. You want to find what's the average, height of people. You take lots of samples of people's heights, and then you construct a confidence interval for the average, that the height looks like it's between 5.5 and 5.8, with probability 95%. So to make that statement, you use the central limit theorem and you use the root n that comes in a big way. That's right. So hence you can come up with this interval, 5.5 to 5.8. If it was more noisy, the interval would be larger.
And bro, how is root n by sigma going to infinity?
I mean, it's going at the rate root n.
Oh, and sigma is something.
Sigma is just a constant, yeah. In reality, constants matter a lot. What you earn 1,000 rupees or whether you earn 1 million rupees, in mathematics, they just don't make any difference. They're all just positive terms. They don't affect the rate of convergence at all. All right. Is this kind of clear? I mean, I'm not going to the statistics of it because one uses the central limit theorem to construct confidence intervals, right? So you've seen that hopefully in some prop stats course, all of you. Okay. Okay. But it's a good kind of ballpark. It kind of tells you that, okay, if I just observe sums of things, if I say to myself, okay, I'm going to do these consulting gigs, I'll have random income, and maybe in 2 years, what's my income going to be? This kind of tells you a very quick way of, okay, it's going to be approximately this plus minus so much. It's a very useful device in that sense. So central limit theorem is very pragmatic, very useful. I mean, you can see a Uber driver can do this very quickly to get an idea of what their income is going to be in 1 year or so. Right? You just look at your past data, you have a pretty good idea what the variance is. All right. Okay. So how do we prove the central limit theorem? How many of you have done a proof of central limit theorem? You've done it. You guys have not seen a proof of central limit theorem. Okay, you won't see it in this class either. But you'll get some inkling towards it. You see some parts of it, I guess. Yeah. All right. So moment generating function is nice here. And characteristic function is a generalized, well, it's builds upon that idea. It's moment of expectation of e raised by I tx. I is a complex number. Okay, so why do we worry about characteristic functions? Why aren't moment generating functions enough? Any thoughts? No, but hopefully we are able to do a lot more with it, right? That's right. So what's a lot more that you think we can do here? Hmm. See, what is moment generating function? Let's just assume that the random variable is non-negative for now. Right? Now, can you tell me examples of random variables for which this is going to be infinity for any t greater than 0? This is empty.
Finite when T is
Huh.
more than log 1 by
What's that?
T is greater than
T is, let's say t is positive number. My question to you is, when is m of t infinity?
X greater than 3 to the power 1 by T X squared. Negative thing.
Just think for a while. No, you're in the right track. Yeah, this integral has to blow up. Huh? So fx, it's a respectable quantity, right? It's a probability density function. Hmm. So anybody? Even the guys who know? Rakshik, can you tell me? I mean, I heard the word mean of ensemble numbers.
Mistake that I know relationships have infinite.
Yeah, so give me an example. Bible does not. No. Nope, nope, no.
For some values of
No.
some values of values.
You look, but you do not see, as they say in Sherlock Holmes setting. Huh?
Can you not just say that fx is any function greater than e to the power 1 minus t?
E to the power 1 minus
Because this will give you some C.
e to the power 1
If you
minus
integrate e to the power some
Yeah.
positive constant.
That's
to
right.
x, that
Yeah.
would-
Right. What are the functions that you know that integrate to infinity? Let's start from there.
Integrate to it.
Yeah.
And go to zero.
Huh?
And they don't go to zero.
No. I can tell you many functions which integrate to something positive. They don't go to 0. You're saying functions themselves don't go to 0. Of course, that will do it. Yeah, constants will do it. Okay, so if my fx made this thing constant, that would work. What are the other functions which are more interesting functions which integrate to infinity, but they themselves are not constants? Yeah, that would work. Huh? Infinite variance. Huh. Yeah. You need to say more than that. E to the power minus x is a flat-like distribution. So that will not work. E to the power minus x squared is also a flat line kind of distribution.
I mean, want something. Maybe minus b is not convergent. Project product should be greater than 1 times a. Then e to the minus b.
Would that do it? This will not? This is infinity, right? Okay, but maybe maybe I was too thin. This also, right? Yeah. So for example, polynomial tails, when you integrate with e to power something positive, that's going to eventually, e to power 0.005x 1 upon 1 plus x to the power n. This will become greater than a constant. It will become greater than 1, for example, right? For x large enough. And then the integral will blow up to infinity. So certainly these polynomial tail distributions have moment varying function which is infinity for t positive. These are called fat tail distributions. Okay? But as you're suggesting, it could be even lighter tail distribution can also have this property. For example, if e to the power minus x, if I take, that's a PDF. And then for t between 0 and 1, no, for t greater than 1, t greater than or equal to 1, the moment varying function will be infinity. But at least in this case, it will be finite till 1.
But if you take e to the minus tx,
Yeah.
then that's forever.
That's right. Then, of course, it's infinity. Yeah. But, more interesting distributions are, okay, maybe if you take e to the power. And I can always normalize this and make this a probability distribution, right? And this will have moment varying function, which is infinity. So the point is, moment varying function for these guys is not capturing too much information. See, the thing is as follows. This moment varying function is a very powerful tool. I mean, it's capturing lots of information. It's capturing all the moments, right? It's capturing all the moments. If I told you this function for, if the moment varying function was finite for t between 0 and say 0.01, then just by looking at the picture of this curve, you can infer all the moments. So it has all that. But more than that, you can actually invert these things and recover the probability density function. So you can actually recover the probability density function from the moment varying function when the moment varying function is finite in a neighborhood of 0. But it can be infinite in the neighborhood of 0, as we saw in the example. So moment varying function is not the right tool. Is this kind of clear? So characteristic function turns out to work really well, much, much more generally for all distributions. Okay? So this will capture, so basically I can invert the characteristic function and recover the probability density function or probability mass function of the underlying distribution. So there's a one-to-one mapping between characteristic function and between the underlying probability distribution or mass function. Is this part clear? It's a signature of probability distribution function. That's why one often works in the spectral space.
And here it need not be in the neighborhood of 0.
It will be finite always. So yeah, that's right. Need not be.
And how just like introducing I to the equation makes it so much like.
Well, because what is this guy? It's just cos of tx plus I times sine of tx, right?
Yeah.
This is just a fancy way of saying this guy. And cos is a bounded function, sine is a bounded function. So now you have a bounded function. So bounded functions I can always integrate with any density, right? So it's very powerful in that sense. So one will play with characteristic functions, but the main thing is to realize that characteristic function uniquely identifies the probability distribution function. So let phi n sequence of characteristic functions for random variables x1 through xn. Then if phi n t for all t, so this is a theorem which I will not prove, converges to phi of t. Yeah, pointwise, as n goes to infinity. And phi of t is continuous around 0. You could have phi of t discontinuous around 0, then things mess up. But if it's continuous around 0, then the associated distribution functions of xi's, fn, are converging in distribution to f, where f is the distribution function corresponding to characteristic function phi. So phi will be a characteristic function of a distribution function f. So this is a very kind of nice, convergence of distribution result interpreted in the characteristic function space. So is this kind of clear? We're not going to prove this, but in a probability course, you will prove this. Yeah. Yeah. I can take phi, invert it, and get f. So they are these inversion theorems. So in the spirit of Fourier inversion theorems. And the other point is characteristic functions uniquely determine the distribution of random variables. So now you're with me on this, right? You're comfortable with this? As comfortable as we need to be at this stage of the course, right? Again, I won't ask you terribly hard questions, so cheer up. So, this course is more about kind of picking up things.
No, could you just accelerate that? So pointwise convergence.
Yeah.
Also for the
Actually, it turns out to be, I'm little, I don't quite remember. I think it turns out to be uniform convergence.
we need uniform.
No, it follows. Go ahead, but let me not comment on that. I'm not quite sure. I don't quite remember it. Go ahead. Yeah, yeah. If the distributions are converging, then their characteristic function will converge. That's a very easy result. Essentially, as such, convergence in distributions, as I said, random variables can also be in different spaces. So there's another result which says that if I give you a sequence of random variables which are converging in distribution, I can construct another sequence of random variables with the same distribution, but they now define on the same space, and they are converging almost surely. Then, because phi is a bounded function by bounded convergence theorem, see, dominated convergence theorem subsumes bounded convergence theorem. So by bounded convergence theorem, characteristic functions will also converge. Okay. This kind of too much. All I'm saying is if I give you a sequence of random variables which are converging in distribution, just assume for now that they're also converging almost surely. It requires work, but then just by boundary convergence theorem, I get that the characteristic functions are also converging.
And that's because you want to
Yeah, that's right.
because you're saying one guy is going to a limit.
Yeah.
And expectation of that guy.
That's right.
Is going to limit, f is bounded, so then.
We can interchange the expectation and the limiting operation, so it all works. Yeah, yeah. Okay. All right. Good. So now what we'll do is we'll basically look at characteristic function of this quantity right here and argue that this characteristic function converges to the characteristic function of the Gaussian distribution. Right, so that's the charm. So in some, and the way the convergence will happen is characteristic function is an expectation Sn minus nbu by sigma by root n. Its characteristic function will do a Taylor expansion. And through Taylor expansion, we show that we have this convergence.
That on. Taylor expansion don't do the same guy. Yeah.
Well, yeah. So let's first compute the characteristic function of normal 0, 1. See, normal 0, 1, first you look at it, it looks like an ugly distribution, right? E to the power minus x minus mu by sigma the whole square divided by 1 by root 2 pi. It's a little messy. But beauty kind of comes in when it look at its homogeneous function or its characteristic function. Then somehow it begins to make sense. Then this 1 root 2 pi which bothers us is just a normalizing constant. All right, so let's do that here. Right? I can write this as follows. I can simplify the integrand. I'm just completing the square. Okay. So all of this works because complex analysis mirrors real analysis for exponential functions. And you get e to the power minus t square by 2. So that's a very nice result, right? The characteristic function of Gaussian distribution mean zero variance 1 is just e to the power minus t square by 2.
So this last already we got because the integrand is just the.
Yeah, that's exactly. Yeah. Yeah, you can define Gaussian distribution with means in complex space. Yeah, things work out. Okay, so you're with me on this. If it was momogenic function, then this would have been e to power t square by 2. Mhm.
Now, the second term looks very similar. Just an observation. The second term looks very similar to what we did in GDA during machine learning course,
Okay, yeah.
where we're trying to just like make sense to how this is an exponential family and then we apply it to PDA.
Yeah, no. I've come to realize that exponential family should not be taught in machine learning course at all. It's a complete waste of time. But yeah, we did similar things, but it's not quite exact mapping. So next time that one section will be completely canned.
Right. The second part, in machine learning course, we show
Yeah, so that.
very similar to exponential
But you're clear in this, right? E to the power itx, e to the power minus x squared by 2. I just make this into a whole square. I get this extra t squared by 2 outside. I keep it here. The remaining thing, it turns out, nicely integrates to 1. That's a big simplification one looks for when dealing with this kind of integrals.
Can be taken. So basically just the Gaussian distribution is not the ideal.
Yeah, that's right. That's right.
That's allowed.
That's allowed. That's allowed. Yeah. I mean, at the end, this integral has to integrate to 1. So the mathematics, does it work or no? It does. And because it does, you can define it. Yeah. All right. So now we know at least what we want to prove central limit theorem, what we want the characteristic function to converge to. And it looks like something you might see in Taylor series, right? T square by 2. Well, if we take a log. Anyway, let's come here. So this is the momogenic function, the characteristic function. And now we exploit the fact that the xj's are independent. Right? So this is just summation j equal to 1 to n, xj minus mu by sigma by root n times t. The summation is there. Summation just gives you this product raised to power n. And now you're left with this quantity right here. This is just, if I think of x minus mu by sigma as my random variable, actually x minus mu is my random variable, then it's homogenic function evaluated at t by sigma by root n. Its characteristic function evaluated at t by sigma by root n. So that's just this quantity.
Expectation to the power n.
Hmm?
You raise the expectation to the power.
Because they're independent, right? So characteristic function of the sum is product of the characteristic functions, right? So you have to exploit that, right? All right, so now it's beginning to make sense. This quantity right here, I can do Taylor series expansion. It's, as n goes to infinity, it's getting very close to 0. So I can do Taylor series expansion around 0. You can check that the derivative of the characteristic function evaluated at 0 is just I times its moment here, fx. See, it's like this, e to the power I t x. I'll just assume density. Now I differentiate with respect to t. I'll get I comes outside x e to the power I t x. Fx dx. And now I put t equal to 0. So this just becomes expectation here, right? That's why these names of momogenic function came up, because you could generate moments by differentiating. Now there was a limit and integral exchange that happened here to do this. Like derivative is a limit operation. So I'm bringing that inside the expectation. We are all friends here. We can do this thing without we don't need to justify these things amongst ourselves. Okay, but needs a mild justification. All right. Don't write that in the exam, huh? Don't be friends there. All right. Okay, now similarly, if I differentiate twice, I get minus e of x squared. right? Very clear. ठीक है? Question or?
About how adding that I makes you think smaller. Yeah, it tells a lot.
Yeah.
I mean, I don't see how. Say,
I mean, in the real numbers, small and big doesn't matter, right? Between 0 to epsilon contains all the information of the whole real line. Yeah. As you have uncountably many equations, so to speak.
say x is an RV,
Hmm.
such that x square is unbounded. E of x, expectation x square.
Yeah.
So let's say unbound variable. Now, if we take the characteristic generating function, over there also it will be this negative.
Hmm. Over it'll be what? Negative what?
Like if you look at
Where you're trying to think about E of x square being infinity? Is that?
okay, wait. Okay, I
Yeah.
messed up.
Yeah. No, it's a fair point that, even I can give you random variables whose expectations are infinity and second moments are infinity. And then these pictures will look quite messy.
But your characteristic for Mr. Bender, that's what matters.
It'll be well defined, but it won't tell you very much. In the sense the first derivative is infinity.
The fact between both characteristics now.
I mean, when we are doing central limit theorem, we assume that the first and the second moments exist.
Right.
If they didn't exist, then the characteristic function will look ugly.
But if they exist, then they exist in a moment that it is right?
I mean, if I give you fat tail random variables, variance can be infinity.
But then that's against our assumption only, right? You assume that the first and second moments are different.
That's right. That's right. No, but
That then you eliminate family altogether.
no. I mean, it's good to have characteristics functions which are well defined for t in the neighborhood of 0, and then do Taylor series expansion on it. Then to take homogeneous function which is not defined in the neighborhood of 0, and then since the moments match at 0, the Taylor series is still meaningful. It's not. ठीक है? Okay. So now we'll simply go ahead and expand this quantity right here. Right? So it's t by sigma root n into the first moment, and t by sigma root n I square into the second moment. And the error terms, again, we're going to ignore here. So in that sense, we're not being rigorous. And one needs to show that these things are really actually small, they don't matter. But we won't be rigorous in that sense. Okay. But this quantity now becomes 1 minus t square by 2n plus something small.
So which one?
Are you with me on this so far? Where did I lose you? This part, okay, that's not so bad. I mean, I'm just doing Taylor expansion of this over t equal to 0, right? So I'm going to keep this quantity here, the argument, into the first moment at t equal to 0. First moment will just be x minus mu, because now I'm looking at random variable x minus mu. And that in expectation is 0. So this term is just going to vanish. And here I'm going to get x minus mu the whole square, whose expectation will give me the variance, sigma square. Okay, so that's where and I square is just equal to -1. So I get this quantity right here. Okay. And this I'm just saying everything else is small.
Yeah, no, that's what I was trying to say. Then you're not really bad.
Huh?
I mean, you shouldn't worry about that, man.
Yeah, you have to worry about that. One can, no, it's not a big deal, but it requires work, yeah.
But what's that second? 1 minus VP, is that part of the first equation? Yeah, it's equal to VP. Okay.
Wait, bro, how did the first one vanish? Like, how did it go to zero?
Because expectation of x is exactly equal to mu. It's a zero mean, x minus mu is a zero mean variable, so it vanishes. Right? So now this limit is what we want to show looks like a Gaussian distribution, right? It should look like the characteristic function of Gaussian distribution.
Oh,
And that's exactly this quantity right here. And that's e to the power minus t square by 2. So you look at SN, sums of many variables, center it by subtracting the mean, divide by variance, so variance becomes 1. The claim is that random variable is looking like Gaussian distribution. And the way to do this is look at the moment Jenny function of this random variable. And that looks like the moment generating function of Gaussian distribution. Hence, or characteristic function, and hence you get the central limit theorem. Big picture, as you've probably seen somewhere in central limit theorem is, I start with distribution like this. I take two terms, it already begins to look a bit like this. Well, with modulo my artistic abilities. I take 5 terms, it looks very much like a Gaussian distribution. So the theory, of course, is that the further away you are from Gaussian distribution, the longer it takes for the central limit theorem to kick in. But the further is not quite in the sense of pictorially how far you are. In the sense that if you have, if your third moment is infinity, although the picture looks like it's Gaussian distribution, it takes longer time for the central limit to converge. So, in the right measure, you have to be far away from Gaussian distribution. But still intuitively, the more uglier your picture is, less symmetric it is, more samples you need for central limit theorem to kick in. But it does kick in. So everybody with me so far? Now we have an idea of how to prove central limit theorem, right? Okay. It's good to know because that's how we'll construct Brownian motion. It's going to rely on the central limit theorem. That's where we get the intuition. That it's, when we sum up a lot of variables, they begin to look like a Gaussian distribution. All right. So let me just state Fubini's theorem to you here. It's, Fubini, yeah. It's not hard to prove. It's just one of the exercises and kind of being careful and going to the indicators and doing the things, step by step. But I'll just state it for you. First, in a simpler setting, so think of g of xy as a function on R squared, right? And the question we're answering is, when can we interchange integrals? Now, because you can integrate with respect to x first and then y, or y first and then x. When can we do this interchange? That's the question being asked. It's like when you're doing double summation. When can you interchange the double summation? Right? Do you know when can you do that? Same conditions work. Actually, it's the same conditions. Yeah. So we want this integral to be equal to, first you integrate with respect to y and then you integrate with respect to x. And same thing, first you integrate with respect to x, then you integrate with respect to y. You want this equality to be true. And this is true under two sufficient conditions. It's always true if your g is non-negative. It could be that both these terms are plus infinity. That's okay. They will be plus infinity together. Or if they're finite, they'll be equal when g is non-negative. Or when absolute value of g of xy, when you integrate it, that's convergent, that's finite. In this case, you can interchange the summation order. Okay? So that's a big result. That's Fubini's theorem. But now we can say this in a much more complicated manner, right? In a much more general space. So that's what we say here. I mean, you kind of have to understand that even here, many things have been said that needed justification. So let's try to give some feel for that. So let's generalize to space omega 1, omega 2. So essentially now I need to define omega 1 cross omega 2 on which my function gxy is well defined on the product space. So R2 is an example of a product space, right? R cross R, right? Now I need an idea of measure, first of all, a sigma algebra on the product space. So I need a sigma algebra on this product space, F1 cross F2, and I need a measure on the sigma algebra. So basically, I'll just say it in words. I won't spend time writing it down, or I won't waste a few more slides on it. You can read up on it if you want to. You don't have to know these things. But the idea is, take every Borel set in F1 and every Borel set in F2 and take the cross product. You got a set? Collect all these sets. And now look at the smallest sigma algebra which contains all these sets. And that's your F1 cross F2.
Can you repeat? As the Borel of F.
Yeah. So I take any Borel set in F1.
Okay.
F1 is a sigma algebra on omega 1.
Okay.
Omega 1 can be real line. F1 can be Borel sigma algebra on the real line.
Sure.
Take any subset there. Take any subset on F2. right? But F1, F2 can be more general, omega 1, omega 2 may measure also.
Hmm.
So let's look at cross product of these two sets,
Hmm.
A1 cross A2.
Hmm.
Collect all these guys for all Borel sets.
Hmm.
That will not be a sigma algebra. If you collect all these guys, it will not be a sigma algebra. But that requires a proof. Well, why it need not be true, right? There could be sets which are
Sorry, all the conditions not like that.
because you may take a kind of a countable union and all that and find a set which is not a cross product of Borel sets like this. So you look at the smallest sigma algebra which contains all these sets. So you expand your sets.
Oh, you expand.
Yeah, yeah. That collection by itself would not do the job, but you expand it to do the job. And that's your F1 cross F2.
Okay, so it basically gives you some base. On top of that, then you can expand and
Put more sets. Yeah, a lot more sets, and then you're done. Okay.
But
And-
why take only this set? Why not take any arbitrary other set and then expand on that? What's the advantage of
You mean why take Borel sets?
Yes.
Yeah.
Like, why take the Cartesian product of these two Borel sets? Why
Yeah.
not just start with any abstract set? Like, what advantage is
Well, I mean, first of all, it's very reasonable to do that. You take all the Borel sets from here, all the Borel sets from there, take the cross product. Now, you could have taken just intervals and just intervals, taken their cross product, that would have been enough.
Hmm.
Intervals are Borel sets can be much more general.
Hmm.
That would be enough. But why we take this? Because these sets we can assign probabilities to.
Oh, okay.
Because mu1, A1 is well defined. A1 is a Borel set, I can assign mu1 to it. A2 is a well-defined set, so I can assign mu2 to it. So then I can come up with a product measure. So when I do this integral here, dx dy, I need to have an idea of a length in this R2 space.
Hmm.
It becomes the area. I need to have that a measure on the R2 space. So I kind of ignore that. We have an intuitive feel for it, but it needs to be well defined. It's the idea of area here, volume in 3 dimensions. But basically, I need to have this idea of a product measure pi A1 cross A2. So what that means is, you define pi A1 cross A2 as follows, and then you use cleverly Calatayud-Rieu's theorem, which will tell you that this pi will expand uniquely to all of F1 cross F2 sets.
One question.
Yeah,
So suppose I have a probability measurement A1 and a probability measure on A2.
that's right.
And then I'm redefining my product measure on this set. So will that the product measure would be some function of mu1, mu2, or would it be like can it be something more abstract than that?
I mean, right now I'm looking to define a product measure of mu1 and mu2. So then it will be this. But your point is on this product measure space, can I define other probability measures?
Yeah.
Of course. You can always do that. Yeah. You'll get plenty of time to come up with changes of measures, different measures on set spaces. Yeah. Is a algebra. Yeah, that you can put. Actually, F1 cross F2, because F1 cross F2, well, because we constructed Cartesian product of Borel sets, what we get, the collection is algebra. If it started the intervals, we won't get an algebra. Anyway, those are details, but that's true. So hence, if we can define this measure on the algebra, which we can, it extends uniquely to the whole sigma algebra. So now all these things are well defined. Now all the headache of what the underlying measure are and all that is well defined, is away. So this quantity now is very cleanly defined. Gxy pi dx cross dy.
This gets like this 25.
Yeah. What we are saying for 2 will be true for any finitely many damage. Yeah. You have to do extra work for countably many. It doesn't automatically generalize. Okay, so now this quantity is well defined. Now the claim is that this quantity here is equal to this quantity right here. So this is iterated integral. I'm first fixing x and evaluating this integral here. So then I need to argue that gxy for x fixed is a measurable function of y. Is a measure, because then I can define integration with respect to any measure on y. So that requires a proof. Then I get this integral here. This integral is a function of x. I need to argue that it's a measurable function of x. So then I can define this integral here. So those are the nuances one has to take care of to be completely rigorous. So then this whole quantity becomes well defined. Just one sec, Gauri. So then this whole quantity becomes well defined. And the theorem is that this is equal to this when your g of xy is non-negative, or when this integral is defined for absolute value of g of xy as being finite. No. We don't need any of those conditions. This result is more generally true. Just that, when you want to show this quantity, then finiteness will play a role. But so there's the idea of sigma finite measures. You've heard these before. Huh? You heard of sigma finite. So like you can break up the space into countable space, and on each part of that space you have a finite measure. So those conditions one does need. Yeah. But why kind of make our life complicated to think of measures which are like very strange?
Sorry, I'm repeating everything. Just put it here.
Uh-huh.
You have F1, F2.
Yeah.
How much amount of space you have an F2, you take the cross product of this. But now this might not be sigma algebra. So you take the smallest sigma algebra to deal with. Now you have phi A1 into A2 is equal to that new one. But this is not defined for you to sigma algebra, but you use a target or
It's defined for algebra.
yeah, but you use a target or
That's right. That's it. Yeah. So now everything is well defined. Now we need to define this integral. Yeah. Yeah. It becomes a yeah. Everything carries through. So you can have a joint integral in n dimensions. And if the integrand is non-negative, then you can also evaluate the joint integral by integrating with one term at a time. Yeah, that's good. So yeah, everything I'm showing in 2 dimensions extends to arbitrary number of dimensions. Finite, integer. So any questions on this so far? Right? Okay. So now let's talk about multivariate Gaussian distributions. How many of you seen this before? Multivariate Gaussian distribution? You guys have seen it. You guys have not seen enough of it? You have seen it. Okay, so most of you have seen it somewhere, right? So when do we say x1 through xn is multivariate Gaussian?
Dependent times. That we should have. The correlation is 0, but they're not independent.
No, that's a separate question. We will eventually discuss that. It's part of the slides. But right now I'm just saying, when do we say that the sequence of a vector of random variables is multivariate Gaussian?
We have to define, what do you call it, a matrix or
The probability as a
I need to define a joint PDF. Joint PDF tells me that it belongs to multivariate Gaussian family. Yeah.
Your PDF is also have a covariance matrix.
That's right. Yeah. So the joint PDF will have the mean and the covariance matrix embedded in it. But I need to give you the joint PDF for this to be true. All right. So this vector V1 through VD is with mean given as follows of this vector, and the covariance matrix given as follows, right? Everybody understands the covariance matrix, right? Sigma ij just means expected value of xi minus mu I times xj minus mu j. Expectation of product. Okay. So it's called multivariate Gaussian if the corresponding density function has the following form here. right? So you can see that, Gaussian was not such an ugly density. It generalizes so nicely in multiple dimensions. So things are quite nice. So you've seen this before, right? These are just normalization constants. All right. And what you start with is this. And then you prove that for these random vector, the mean is given by mu. That follows from this representation. And the variance covariance matrix is given by sigma. That follows from this representation. Right?
So the denominator of the densities are the determinant of the
That's the determinant of the covariance, square root of the determinant. Yeah. So this requires a proof. Right? First of all, you have to prove that this is a joint density function. So if you integrate this, it should integrate to 1. That requires a proof. Then you have to find the mean and show that the mean is mu, variance covariance is that sigma. I'm assuming all of that. Yeah. That's
Not
right.
just that P extra is one. That we saw that if you just integrate one there, that gives the PDF.
This will be true by definition of joint PDF.
No, to show the joint PDF, you need to show that.
Yeah, to show the joint PDF, you can use you can do Fubini. Fubini is telling you that the joint integral can be evaluated iteratively. Yeah, that's right. So that in that sense, we look at. So in that sense, the iterated integral will become 1. Okay, now if you simplify to 2 variables, you get the following form, which you may have also seen already, bivariate Gaussian distribution. So f v1 v2 has the following form here, where rho is now the correlation coefficient. Everybody knows what the correlation coefficient is? I don't need to write it down. Okay, let me write it down. It's sigma xy upon sigma x, sigma y, where sigma xy is expected value of x minus mu x, y minus mu y. Right?
All we're saying is the covariance is all 0.
What?
All we're saying here is that rho is 0 because the covariance.
Yeah. I mean, that's all we're saying, but that's one thing we're going to say. Yeah. Right. Okay, but yeah, to you're I guess addressing this point right here. If rho is equal to 0, then just by the form of the joint PDF, we get that the joint PDF becomes a product of the individual PDFs. Right? And that immediately implies that the 2 random variables are actually independent. So in this case, being uncorrelated, that means rho is equal to 0, implies that the random variables are independent. Not always true. But because it was bivariate Gaussian, this turned out to be true. And just because we could write this as a product of 2 densities. Everybody's with me on this, right?
So let's say we get a trivariate Gaussian distribution.
Right.
And then we define P12 as the correlation between x1, x2, and P21, and then P13.
Yeah.
तीनों का कराओ, तीनों 0 है. Then
Yeah.
V1, V2, and V3.
That's right. So multivariate Gaussian will be independent variables if the variance covariance matrix is just a diagonal matrix. If the, what's that?
Then it's just
In that case, they're perfectly correlated. Yeah, so they're not independent in that case, right? Perfect correlation does not mean independence.
I think the problem you gave was this is the expectation of times
Yeah.
x minus mu divided by the independent x. So if x and y are independent, then nothing go equal to 1.
If x and y are independent, then the numerator is 0. Covariance is 0. Right? Yeah. Okay. All right. Okay, so far so good. I can move the slide. All right. So this is the example that you may remember from the last class, some of you. Uncorrelated but dependent Gaussian random variables. Gauri, have you seen this before? Okay. X and Y are both normal 0, 1. X and Y are uncorrelated, but they're not independent. Can that happen? So guys on this side, is this the first time you're seeing this? Okay, so now the question is clear, right? You have to give me two random variables X and Y. They have a Gaussian distribution. They are uncorrelated, but not independent. Huh. Do you remember this?
I mean, I've seen the lemma where independence implies uncorrelatedness and
Yeah.
uncorrelatedness doesn't imply.
Unless you have a bivariate Gaussian setting.
Hmm.
In bivariate Gaussian, uncorrelated also implies independence.
Oh,
That's what we showed last time,
yeah.
because the joint density became the product of densities. So clearly, we are not in the bivariate Gaussian setting when I'm giving you this example,
Hmm.
right?
So,
So does anybody remember how to do this?
But you also skimmed right now, so I kind of saw it again. But I remember.
Okay, all right. Chalo, so let's just see this here. So let's X be normal 0, 1. Let Z be a random variable which independently takes two values, +1 and -1 with probability half each.
Hmm.
Then let Y be equal to Z times X. Okay? So what's the distribution of Y? Y is sometimes X, sometimes it's -X,
I expected.
right? But turns out it's still normal 0, 1. Why? Because how do you show that? Because you have to look at the distribution function, right? And that's just the distribution of Z times X less than or equal to X.
Hmm.
And that's Z is equal to 1 and X is less than or equal to X. Or Z is equal to -1 and X is greater than or equal to -X. Okay. Half times this quantity plus half times this quantity. And because Gaussian is symmetric, both these terms are exactly equal, right? If I show you this picture here, then this mass here is same as this mass here, right? X going left side minus X going right side, same. Okay. So X and Y have the same distribution. How do we show that X and Y are uncorrelated?
Expectations.
We take the covariance, right? Okay, what's the covariance equal to?
Over here is expectation the end the mean of both gallery.
Expectation of XY is expectation of X times ZX, right? That's expectation of Z times expectation of X square. The independent Z and X square are independent. So E of Z times something positive, but that's E of Z is 0. So they're uncorrelated. If I tell you the value of Y, X can take two values on both directions, plus as well as minus. So EX, EY is equal to 0. But now they're not independent. Why are they not independent? Oh, sorry.
I mean, fixing X specifies Y.
Right. If I tell you X, I've told you a lot about Y, right? If I tell you X is 0.5, then Y is either 0.5 or it's minus 0.5. So you get a lot of information. So in particular, Y square is exactly equal to X square. So if I tell you X square, I tell you what Y square is. So they're not independent at all. Right. So we need to again ask ourselves, how should we define independence so that this doesn't satisfy independence? We've not really defined independence very clearly so far, right? So we'll do that next time. So we'll spend some time defining what independence means and all of that. And then because once we appreciate that, then we can talk about conditional expectations. So where we're going with all this is we want to do conditional expectations. Those are kind of building blocks for martingales. Martingales are building blocks for stochastic integrals and for Brownian motion. That's where all this is. That's right. Yeah. Well, E of X is 0 and E of Y is 0. It's a double whammy. You know?
Okay, right.
No. Double engine zero, yeah. Okay. But you can see what's going on here is that the mass is, if this was bivariate density function, then any areas here will have positive probability. But in this case, all the mass is lying on these lines. X is this, Y can take just this and this value. So it can't be bivariate density function. It's putting all the mass on a set of measures 0 and 2 dimensions. All right, so we'll take this up next time. Any questions, guys, on online? All right, then I'll see you day after tomorrow. Bye, Akhilesh. Bye. I'm just
Bye, sir.
Yeah, bye. I don't see too many other familiar faces here. I'm trying to see Gaurang. Oh, I don't see him. I guess people are just seeing the video now. Bye, everybody. Yeah.
Bye, brother. Thank you.